So this is part 3 of Dr. Osbey's Fundamentals of Aerodynamics project with the semicircle flow, viscous and inviscid flow. So first we're going to start in the design modeler in Fluid Flow Fluent. And since it's a 2D flow, we're going to go into our XY plane. So we're going to start with a giant rectangle. And so I'm going to dimension this top line as 40 meters. And then the height of the rectangle as 20 meters. And then now I'm going to take a construction point, put it on my line, then add a midpoint constraint from here to that line, and now we have that point at the center of the line. Next, what we're going to do is make this circle, and then we're going to give it the radius of 10 meters, as is in the handout. And then the final part, what we're going to do to finish the geometry is trim this bottom portion and then these side pieces here. So now we're going to go to Concept, Surfaces from Sketches. We're going to choose this, Apply, and Generate. And now we have our semicircle model. Next, we're going to go into Workbench and we're going to begin the meshing phase. Again, we're going to go back to 2D, and the first thing we're going to do is start by creating name selections. So we're going to do we'll call this semicircle. We'll call this the inlet, and then the pressure outlet, and then these last three will just be walls. And there we are, we have the beginning of that. Next thing we're going to do is insert a mesh, apply it, and now we're going to begin using triangles, and we will generate that. Next, we're going to change the element size to 0. For this, we will do 0.5 just for the sake of time. In my actual one, I did 0.15. And then we're going to generate. And now we've got kind of small ones here. The next step, what we're going to do is we're going to go right click, insert, and we're going to do sizing, and then we're going to choose edges to size. So we're going to do one. All of these exterior edges we're going to size, and we'll change that to like 0.25, and then we will generate. And then the final thing we're going to do is insert a refinement along the total geometry here, and then generate. So now we have a much smaller, nicer mesh here. So now we're going to go back to Workbench, we're going to update our mesh, update our downstream, and we're going to begin the solution setup. I use double precision and 2 solver processes. You can do single and 1 solver process, or any sort of way you'd like to do it. So now we're going to set the model. So I'm going to show the inviscid case first, and then the process for the inviscid model will be exactly the same, or for the viscid model will be exactly the same. It's just changing a couple more settings, and I'll show that towards the end. By the handout we are given, the free stream velocity is going to be 25 meters per second. So we're going to go to boundary conditions and then change that to 25. The outlet, we're going to go, just click we're not going to do anything but prevent reverse flow. Now we need to change the density of air to 1.2. Go to materials, go to fluid, go to air, right click edit, and we're just going to put this to 1.2, change create and close. And now we have our inviscid flow simulation set up. So I'm going to go initialize, more settings. I'm going to change this to 50. And then number of iterations, we'll do 150 for the calculation itself. And we'll initialize and calculate. Alright, we'll see that it has converged. So, the first step is we're going to get our contours. So, I'm going to start with the velocity contours, and we're going to leave everything open there, and change that. And so this is the velocity contours for the inviscid flow over the semicircle. You would do this same process for the pressure, so we'll just go and change this. We'll go, we'll just do a new contour here, and we'll call this pressure, and we'll show the dynamic pressure for this one. So this is the dynamic pressure, and then again, you know, we want static pressure, we go to static pressure. We want total pressure, we'll go to total pressure, and all of that. Now we want to show the pressure coefficient and velocity distribution across it. So this is where making those name selections are going to come in very handy. So we're going to do the velocity distribution first, and so we're going to do it, we're just going to do the semicircle right there and plot. So if I move that down, we'll see it, the velocity distribution kind of vaguely looks like the top of the semicircle, which is true for a inviscid flow. It will change as we go across the distance. It'll speed up rather from the stagnation point down here as you go across and then return back down. Now we're going to do the exact same thing for the pressure coefficient. So pressure, this drop down, pressure coefficient across a semicircle, and again, now we have what looks like the opposite, right? So remember, for an inviscid flow, it should be bound between 1 and 3. Of course, between this, it's close, but it's not exact. That could just be the computational errors and cutoffs and rounding. But overall, the shape is what's most important here, in that it starts at one point and then returns back to that point in an inviscid case. Now, finally, what we're going to do is get the drag coefficient and lift coefficient. So we're going to go to the left under Results, under Reports, Forces, Edit, right-click. So it's important to know, of course, drag is only in the x direction. So x equals 1, that's your drag and drag coefficient. Y equals 1, x equals 0, that's your lift coefficient. So we'll start by showing the drag coefficient. And so now we'll see down here we have our pressure drag, and remember, it's inviscid, so there is no viscous drag. There's no drag across the body. And then this is the total pressure. And then same thing over here is the the coefficients. So your drag pressure, your coefficient, your drag coefficient due to the pressure is here. Again, 0 viscous, and then your total over on the right. So this would be your drag coefficient. However, these are not always correct, so it's best to take your total forces here and then manually non-dimensionalize them in Excel or anything like that, which is just taking the force and then dividing it by the dynamic pressure. So now I'll show the lift coefficient. Same thing. Again, inviscid, so we only have pressure, 0 viscous, your total drag or your total lift, and then the coefficients that go along with those. Again, it's better to non-dimensionalize them yourself rather than taking these coefficients, because these are not correct. So that is basically the entirety of the part 3. However, so when we go to change the model to a turbulent model, going to use K epsilon, and we're going to do enhanced wall treatment. Then we're going to hit OK. And then nothing else has changed. We can just go ahead and rerun, initialize and calculate. Alright, and our solution is converged. And again, just to show the differences, we'll just go to the first contour here. So this is the velocity, right? So again, it's viscous, so the no-slip treatment is there, which is highlighted when you see that blue going across the line. And then the formation of that wake region back behind here. And then if we want to pay attention to the top, which isn't, you see a kind of a boundary layer forming. So the thing is exactly the same, the procedure is exactly the same, and that's how you do part 3 for the project.